Dr. M.C. Sundaraja. He completed his undergraduate studies from Madurai Kamaraj University and went on to complete his master's in structural engineering from the same. He is a doctorate from Anna University and he's also done his postdoctoral fellowship at the Queensland University of Technology, Australia. He has more than 17 years of experience in the teaching profession and he has also published papers in 39 international journals, 7 national journals, 27 international conferences and 51 national conferences. He has so far published 124 papers in various journals. He went on to receive the Best Research Paper Award from IFERP, a unit of VVERT and NIRE on 4th April 2015. He has also received Outstanding Faculty Award from the Venus International Foundation Faculty Award, VIFFA, in the year 2015. Currently, Dr. M.C. Sundaraja is now working as an assistant professor in Tyagarajar College of Engineering, Madurai.
Welcome to UGC lecture series on B architecture. In the previous lecture, we have seen the design of simply supported slab, which is a rectangular simply supported slab which is supported on 4 sides which do not have any adequate provision to resist corners from lifting. In this lecture, we are going to design the two-way slab, that is a restraint slab, which is having proper adequate provision to resist corners from lifting. So, here in this also we are going to calculate the total load on the slab. Before it, we need to find out whether our slab is two-way slab or one-way slab from the ratio Ly by Lx. If the Ly by Lx is less than 2, it has to be designed as two-way slab. Then using load as well as the span of the slab, we are going to find out the bending moment as per IS coefficients, which is given in table 26. The simply supported slab, the table 27 has to be used for finding out the bending moment coefficient, and for restraint slab which have adequate provision to resist the torsion, we need to use the table 26 for finding out the bending moment coefficient, and also using that we can find out the bending moment. Using the maximum bending moment, so here in the case of restraint slab, we are going to find out both negative as well as positive moment along both the direction. We are going to get 2 moments in each direction. From the moments, from 4 moments, we are going to select the maximum bending moment to find out the effective depth of the slab. In the case of reinforcement, along x direction, we are going to have 2 moments, and from the 2 moments, we are going to, that is negative as well as positive moment. From the 2 moments, we are going to select the maximum bending moment for the reinforcement, which is used to find out the reinforcement in the case of x direction. And along y direction, we are also having we are also going to have 2 moments, that is positive as well as negative moment. From among 2 moments, we are going to select the maximum bending moment for finding out the reinforcement along y direction. Finally, we are going to check the depth of the footing against deflection, and also we are going to draw the reinforcement detailing in the case of restraint slab. So, here the problem is analyze and design the reinforcement required for a two-way simply supported slab supported on all 4 sides when the corners of the slabs are prevented from lifting, though it is called as restraint slab. The clear dimension of the room is 4 meter by 4 meter and with one long edge discontinuous. The condition is given in the problem is one long edge discontinuous. It is supported on 230 mm thick wall. Live load on the slab is 3 kN per meter square, and consider other dead loads also. Use M20 and Fe415 as materials. And this is the table 26 which is given in IS 456 for the restraint slab, which is having adequate provision to resist the torsion. So, here the condition given in the problem is that one long edge discontinuous. So, here one long edge discontinuous, the third case. Using this one, we are going to find out the respective moment coefficient for x direction as well as y direction for negative as well as positive bending moment. Using the bending moment, we are going to find out the effective depth of the slab as well as the reinforcement required for it. So, here the clear dimension of the room is 4 meter by 4 meter, and the effective dimension is supported on 230 mm wall on all 4 sides. Effective dimension of room is 4.23 meter by 4.23 meter. The condition for the two-way restraint slab is one long gauge discontinuous. This is a condition. Now, here as usual we are going to find out the ratio, that is L y by L x, that is equal to 4.23 by 4.23, which is equal to 1, which is less than 2. It confirms that it is two-way slab. So, it is square slab, we also confirm it is two-way slab. Next, first step, load calculations. First one, dead load. For the dead load, first we need to assume the thickness of the slab from the deflection criteria. So, here the dimension of the room is more than 4 meter, that is we need to follow the usual the L by D, that is effective depth ratio for simply supported slab, that is 20. So, L by D ratio here it is D is equal to L by 20, that is 4230 divided by 20 is equal to 211.5 millimeter, and overall depth of the slab is 211.5 plus 15 plus 10 by 2, that is 231.5 millimeter, that is 20 to 31.5 millimeter. But I am going to keep the overall depth of the slab as 150 mm. So, normally we need to assume somewhat more than the depth which is required from the deflection criteria, but anyway that based on my experience I am keeping depth equal to D equal to 150 mm. I am going to check the depth of the slab against the bending as well as against the serviceability criteria. If it is not safe, we need to again redesign by assuming somewhat more than the thickness which has been assumed in the first one. Okay. Next, the self height of the slab. Self height of the slab is 0.15 into 25, which is equal to 3.75 kilonewton per meter square. Then in addition to that, they have asked us to consider other dead loads also, that is self height of the slab, then self height of floor finish. So, I am going to provide the floor finish of thickness 0.025 and the concrete flooring, the unit weight is 24, that is equal to 0.6 kilonewton per meter square. And the weight of, in addition to this, I am also consider the weight of partitions. The weight of partitions here it is 1.96 kilonewton per meter square. Now, the total dead load W d, which is equal to 6.31 kilonewton per meter square. And here dead load we have calculated the live load on the slab which is given in the problem. Live load on the slab W L, which is equal to 3.0 kilonewton per meter square. Now, we are finding total load on the slab. Total load on the slab W is equal to W d plus W L, that is equal to 9.31 kilonewton per meter square, that is all. Next, second step, bending moment calculation. In the case of bending moment, now we are going to use the table 26 to find the moment coefficients for the ratio L y by L x is equal to 1. So, L x by L x from the table, that is from table 26 and with the condition of one long edge discontinuous. So, alpha x is for first one is here one long edge discontinuous, this is the short span coefficients alpha x. First one is the negative moment coefficient, that is alpha x negative moment coefficient. Negative moment coefficient alpha x is, that is for 1 is 0.047, sorry, one long edge discontinuous 0.037. Next, positive moment coefficient at mid span. Positive moment coefficient is 0.035. There are two moment coefficient along x direction. then alpha y, that is long span coefficient in the direction y, that is called as alpha y for Ly by Lx is equal to 1. So, here for any ratio, that is any value of alpha x, that is any value of Ly by Lx, the negative moment coefficient in y direction is negative moment coefficient in y direction is one longer distance 0.037 and positive moment coefficient is, that is 0.028. So, here the moment coefficient along x as well as along y directions are same. So, here to find out moment, that is mx and my. Mx is alpha x w Lx square, my is alpha y w Lx square. So, here we are having 2 alpha x and 2 alpha y. From 2 alpha x we are going to select the maximum alpha x, that is 0.037 w Lx square. Here also we are having the maximum value as 0.037 w Lx square, that is equal to. So, here the maximum bending moment is 5.88 kilonewton meter, 5.88 kilonewton meter, that is 0.037 into the total load acting on the slab is 9.31 into Lx is 4.23 square, that is 5.88 kilonewton. So, here mx which is equal to my which is equal to 5.88 kilonewton meter, that is all. So, here mu x which is equal to mu y equal to 1.5 into 5.88, that is equal to 8.82 kilonewton meter. So, this is the way of calculating the bending moment coefficients for a two-way restraint slab, which is having adequate provision to resist torsion at the corners. So, here the condition of slab is one long edge discontinuous, other 3 edges are continuous. So, that is why it has both negative as well as positive moment along both the direction. They are given bending moment coefficients along x as well as along y direction for both negative and positive signs. So, here mx and my we have calculated. Now, we need to next step, we need to find out, third step, we need to find out the effective depth of the slab, effective depth of slab. So, by here I am going to consider 1 meter width of the slab. Normally, we are designing the slab for 1 meter width and the same has to be adopted for entire area of the slab. And also by consider a balanced section. So, by equating mu maximum to mu limit, that is mu is maximum is equal to mu limit which is equal to 0.138 FCK BD square. So, D is equal to square root of mu maximum divided by 0.138 FCK B. So, here mu maximum is 8.82 kilonewton meter into 10 to the power 6 Newton millimeter, 0.138 into 20 into 1000. We are considering 1 meter width of the slab, that is equal to D is equal to 56.53 millimeter, which is less than 180 millimeter, that is assumed value. Hence, it is safe against flexure, that is limit state of collapse. Next, we need to check the depth of the slab against the limit state of serviceability. We need to first find out what is the area of reinforcement required for the slab. So, here third step we have found the effective depth of the slab, fourth step area of reinforcement along both the direction. So, since mu x is equal to mu y, the reinforcement along both the directions are almost same. So, here mu x is equal to mu y. So, along both directions, since mu x is equal to mu y, the reinforcement along both the directions are same. So, which is equal to 0.87 Fi AST into d minus 0.416 XU, where XU is equal to, we know that 0.87 Fi AST divided by 0.36 FCK B. So, when you substitute all the things, 415 into AST divided by 0.36 into 20 into 1000, which is equal to 0.05 AST, sorry 0.05 A, that has to be substituted in the equation. Now, mu x is 8.82 into 10 to the power 6 equal to 0.87 into 415 into AST into d minus, d is 180 minus 0.416 into 0.05 AST. So, by solving this expression, we get a quadratic equation, that is AST square minus 6249.87 AST plus 1.17 into 10 to the power 6 is equal to 0. So, by solving this expression, we get the two roots. We are going to select the minimum root, since it is designed as a singly reinforced rectangular section, that is 193.177 millimeter square. Now, anyway, I am feeling that this is AST is very less. I am going to check this AST with the minimum AST as per IS 456. So, minimum AST for tar steel is 0.12 percentage of gross area of concrete, that is 0.12 into 180 equal to 360, I think that, sorry 156 millimeter square, again it is, which is less than 193.77 millimeter square. Hence, AST required is 193.77 millimeter square. I am using 8 mm diameter bar, 8 mm diameter bar, then I am finding spacing of reinforcement, pi by 4 into 8 square into 1000 divided by 193.77, that is equal to 260.21 millimeter. Now, this spacing has to be again checked with the maximum spacing, check for maximum spacing as per IS 456. The maximum spacing should not exceed 3 times the effective depth of the slab and 300 mm, whichever is less. 3 into 180, that is equal to 540 millimeter. I think we have used the thickness of the slab is 150 mm and small d is 130 mm. And here, when you find the thickness of the slab against the bending moment, it is 56.53, it should be less than 130 mm. So, here and also the expression we have to use here, it is 130, by using that one we got 93.77, and the minimum AST here it is 130, that is, which is 156 millimeter square, which should be less than 193.77, and here also hit 3 times the effective depth of the slab is, that is 390 millimeter and 300 mm, whichever is smaller. So, here this 300 mm is somewhat greater than 266.21, hence adopt 8 mm diameter bar at 230 mm center to center. So, here AST provided, that is pi by 4 into 8 square into 1000 divided by 230, which is equal to 218 point. This is the this is the reinforcement which has to be provided on both directions, since it is square slab. So, 218.55 millimeter square. So, this is the AST we have provided along both the direction. Now, we need to check the thickness of the slab, that is depth of the slab against deflection, that is against serviceability. So, here L by D ratio is equal to 20. This has to be again modified by multiplying with the modification factor. I have already told you that this modification factor has to be found from the figure 4 of IS 456 2000. It has several numbers of, that is 4 or 5 curves, depends on the stress which is developed in the reinforcement, and this graph which shows the modification factor versus percentage tension reinforcement. In order to find out the percentage tension reinforcement, first modification factor, we need to find out the percentage reinforcement, that is AST provided divided by B into D. 100 into AST provided, here it is 218.55 divided by, we are considering 1 meter width of the slab and the effective depth of the slab is 130, that is equal to 0.17 percentage we have used. Next, the stress in steel is 0.58 Fi AST required divided by AST provided. So, that is equal to 0.58 into 415 into AST required is 193.77, AST provided is 218.55, that is equal to 212.75 Newton per millimeter square. So, by referring the figure 4, by using the percentage of reinforcement and the stress developed in the reinforcement, the modification factor here it is 2.0. So, D is equal to L by 20 into the modification factor, that is here it is 4230 divided by 20 into the modification factor 2.0, that has to be 103.25 millimeter, which is less than 130 millimeter. So, here it is safe as well as economical cross section. The basic aim of structural design should be the structure should be safe as well as it should be more economical. So, here when you compare 103.25 with 130, it is most economical cross section. So, here we are going to adopt the depth of the section as 150 mm and effective depth of section as 130 mm, and the reinforcement is 8 mm diameter bar at 230 mm center to center. Now, we need to see the reinforcement detailing. So, here it is a square slab, it is a restrained slab. So, here this is the straight bars and these are all the cranked reinforcement, and this is the main reinforcement in another direction, that is y direction. Both the reinforcements are same since the size of slabs is Ly by Ly is equal to Lx. So, here this is 4.23 and another direction is 4.23 meter. So, here this is and this reinforcement also 8 mm diameter at 230 mm center to center. An alternate bar has to be cranked from the face of the support from the face of the support as 0.1 L. Here also it has to be cranked at 0.1 L from the face of the support. So, here if you take this as the plan view, if you take, so the reinforcement has to be provided along both the direction. And here that is all. This is a plan view which shows the reinforcement. This is a cross section of the slab which shows the reinforcement. So, here the main reinforcement along both the direction is 8 mm diameter bar at 230 mm center to center. So, since it is a restraint slab, we need not provide the reinforcement at the both corners. It is prevented from lifting. So, we need not provide the torsion reinforcement at the corners. Now, we come to the end of the lecture. Let us summarize this lecture. That is, in this lecture we have seen a problem which is used to design a two-way restraint slab for a room of size 4 meter by 4 meter, which is resting on 230 mm thick wall. So, it has an adequate provision to resist the torsion at the corners, and also here we have seen the design of the slab, that is the design consists of thickness of the slab as well as the reinforcement detailing. So, from the reinforcement detailing we have understood that how to draw the reinforcement detailing, how to distribute the drawing to the field. In connection with this lecture, the questions are: design a two-way reinforced concrete floor slab for a room of size 5 meter by 6 meter when the corners of the slabs are prevented from lifting and subjected to a live load of 3 kilonewton per meter square. The load due to the floor finish is 1 kilonewton per meter square and the partition is 2 kilonewton per meter square. Use M20 and Fe 415 as materials. So, for this one we need to select the bending moment from the table 26 from the case 9, that is 4 edges discontinuous. And the second one, design the reinforcement required for two-way simply supported slab for room of size 5 meter by 5 meter clear. It is supported on 230 mm thick wall. The live load on the slab is 1.5 kilonewton per meter square. The condition is 3 edges discontinuous, 1 short edge continuous. So, here and consider other dead loads also, use M20 and Fe 415 as material. So, for this problem we need to select, that is 3 edges discontinuous, that is 3 edges discontinuous, 1 long edge, 1 short edge continuous. So, we need to select the 8th case for finding out the moment coefficients for finding the bending moment along both the direction. And with in connection with the references, IS 456 2000, that is plain and reinforced concrete code of practice, and another code book which is used to select the design loads for the buildings and structure, that is IS 875. Then another book which is used to draw the reinforcement detailing of the slab, that is SP 34 1987. Then we can refer to books, that is reinforced concrete designed by S N Sinha and reinforced concrete designed by Ashok K. Jain. So, these two books are most important. They have explained the theoretical part of this analysis of the slab. So, we can easily understand how to provide how the slab will be deflected, how to provide the reinforcement at the respective places. Thank you very much.